3 at the moment, but hopefully more people will join in or watch the video later. So I'm really addressing them. And out of the 3, 2 are my graduate students, and one of them is an undergraduate, was an undergraduate in my class. So I know the 3 people that are listening right now. And I might as well talk directly to Matthew, who is in the audience and is one of my students. So this is really a talk aimed at trying to communicate what is that we are trying to do with this research. I put it. I mean, the talk series is called "What's Next," implying that something big has already happened and that we are trying to do something after that. Nothing has actually happened yet. Like everything that we wish to do is ahead of us. We just got some funding. We have to still execute the project and follow through with the ideas so that we can see that idea actually in action and producing some impact on research and generally the society. So I titled the talk as questions. I'm asking, how do small grains get charged in a plasma? How do charged grains behave collectively? I put this as question, and hopefully by the end of the presentation, I can give you our approach to answering these questions. Okay, that's what I'm trying to do here. It is motivated obviously by this early career grant from the Department of Energy, Office of Fusion Energy Sciences, which is a substantial amount of funding, $750,000 over 5 years until like 2025. And this is support for 2 graduate students and 2 undergraduate students. So any students who will listen to this presentation, I'm looking for interested, talented people to work with us and try to take this research forward. So Matthew, if you're listening, this is basically an invitation for you to consider working with us. Okay. It is a mandate to establish collaborations and to become a leader in the field. That's what the term early career grant is used to denote. It's supposed to encourage people who have some potential, which has been vetted through the proposal and review process. And then the proposal or the project itself is called thermodynamic and transport models of strongly coupled plasma. So that's what we are working on, and I'll explain what those terms mean. So we are interested in this topic called complex dusty plasma, which you can think of as a system where you have different components, like I'm talking about a partially ionized gas that contains dust particles. So what are we talking about as a partially ionized gas? We know what is a gas. It contains molecules, and then we pass radiation or laser or some kind of electrodes and create ions and electrons, or basically the process of ionization. So we have gas molecules, we have electrons and ions that are charged particles. The electron is negatively charged, ions could be positive or negative. And then if there are dust particles, like these are grains that are small, about 1 micron or smaller, or maybe a little larger, we have a system in which there are 4 components. So neutrals, electrons, ions, and then dust particles. We call such a plasma system as a complex dusty plasma. Why is it complex? Because it involves 4 different species. They all have different masses. If you think about it, the electron is the lightest, the neutrals and the ions are about similar mass, and the dust is much, much heavier than any of these. So we have like electrons, and then we have the neutrals, and then we have the dust particles, which are about much, much higher in mass than the species. So that creates very complex interactions or collisions between these species. And that's what makes this study very rich and very interesting. And these dust particles, they become charged. They acquire lots of charges. They become negatively charged. They carry, each dust particle carry thousands of electrons of charge. And that's because in a plasma, the electrons, which are much heavier, they move much faster than any other species. So they kind of reach a dust particle in more numbers than ions, which could be positive. And as a result, these dust particles are mostly negatively charged. And once they become negatively charged, they start interacting. An example is shown here about the rings found in around Saturn, where fine dust particles organize together and they go around the planet in an orbit, and they are all interacting with each other. That is, if we have more and more dust particles that are charged, they all kind of repel each other, so that causes an interaction. That's what we call an interaction. That is one object talking to another through a force. That's what we call as interaction. So these particles are electrically coupled, meaning if I move this guy, this other guy also moves. It's a result because they are always exchanging forces between each other, and this is what causes them to interact. Now, why should we study all this? That's the question that anyone would ask when they start doing something. It's because that dusty plasmas, the complex dusty plasmas, are very important in astrophysical context, where you have like these rings around Saturn or stars or sun. And they are also used in earthbound systems like semiconductor manufacturing. Like even if you don't like physics, you like your smartphone, you like your gadgets, you like your semiconductors. And to make them, we need to understand how plasmas work. So you can't get away from plasma science without, if you want to ever use technology. And then we use these systems in the laboratory to study different types of physics. And here is a setup that exists at Auburn University, who is one of our collaborators. And we try to understand what happens in controlled experimental settings to do theory about it, to do scientific analysis. More than all these motivations, one very big motivation, a personal motivation for me, comes from the fact that understanding plasma science is the key to realize nuclear fusion. Now, you would have heard about nuclear fusion a lot about in the past several decades. If you are very young, I'm sure you would have heard of this term somewhere. Nuclear fusion is a way to produce energy without any carbon emissions. It's a zero emissions power source. And recently I put this news because it's very recent. It's in the last 2 months. And what we have is basically that MIT has started a project that will produce compact fusion reactors. That is, these reactors are no more bigger than, let's say, the size of a small apartment, and they are supposed to produce energy that has zero emissions, that can power maybe like a small grid, or maybe a few streets, or maybe half of a city, without involving extensive capital expenditure. That is, you don't have to spend billions and trillions of dollars. You can maybe spend millions of dollars, and million with a M, and try to get energy out of this, and in a clean way. Now, why is understanding plasma science important for that? This is the same process that powers the stars, and including our sun, where the nuclear fusion process takes place, and as a result produces energy. Now, I'm not going to give you a lecture on what is nuclear fusion. In simple terms, it's basically two light atoms fusing together. That's why it's called fusion. And once they are fused together, they release some excess energy. And when a lot of these fusion events happen, a lot of energy is released, and you know how hot the sun is, and it's the energy source that powers all the stars. And in fact, the study of plasma science is quite interesting, because it so happens that more than 99% of the universe exists in a state of plasma. That is, in a state of ionized gas, which is very hot, which is what, even though for us it feels like our worlds are mostly solid, liquid, and gas, it is actually more plasma than you could ever imagine, because the size of the universe is so big. So if you want to learn about the ongoing efforts to understand nuclear fusion and how to use it as a power source, I strongly recommend that you visit this site, iter.org, where you can learn about this whole process and all the rich physics that comes with it. Now, where do we come in here? Now, I told you about this very recent effort by MIT to start compact fusion reactors. And what is the big challenge here? That is, what do we want to do? Is that the basic laws that are needed to, are the basic laws that must be understood to make fusion possible are already known. They have been known for really more than 60, 70 years, but still we have not yet been able to create that nuclear fusion reactor that is self-sustaining, that can run for several days or several months, and produce clean, limitless energy. That's been the challenge for about 70 years. And what I believe, this is what I said when somebody asked me about this, is that we already know the basic physics. We have to think about more engineering breakthroughs, so that the job of physicists in doing this is about half done. There is still a lot of job left for engineers to work on this, to make this possible, to take it from drawing boards to living rooms. Okay, so it's more of an engineering challenge to scale all the difficulties. And then what is that we need to do, or what is it that I am trying to do as part of this effort to produce clean, abundant energy, which is that if you have a fusion plasma, which I've drawn here as a sketch, if you have a fusion plasma, the size, whatever the size of your reactor is, you have a hot plasma that I've drawn like a potato here. It's very hot. It's like 1,000,000 degrees Kelvin. Okay, and then you have a reactor that is coated with lead or some kind of material that can withstand so much heat. And what happens is that this hot plasma ejects heat. This heat eventually ablates or evaporates the surface of your reactor. So you have vapor forming here. That vapor comes back into the reactor. It condenses to form small particles, and these particles fall back into the plasma. So what happens is that one of the problems that we have is that hot plasma evaporates the wall, creates small micron-sized dust particles, or maybe even millimeter-sized dust particles that fall back into the plasma and soak up energy that should have gone out as your power generated. That is, you are having impurities that take up energy, and then you don't have enough energy production, and ultimately that extinguishes the entire plasma, resulting in extinction. So the goal is simple. That is, the big picture goal is simple. If you want to if you want to solve the world's energy and climate problem, what you need to do is to understand how to tame nuclear fusion, how to make it happen in a way that is sustainable, that is easy. Okay, that's the big picture goal. What is that we are trying to do is to understand how dust particles behave inside a plasma. That is, if you take charged particles, if you inject them into a plasma, they become charged. I'm sorry, if you inject particles into a plasma, they become charged, and they start behaving in a very, very unique way, and that we want to understand how they behave. Now, if I show you this picture, and if I don't tell you anything, if I'm not here, you could actually mistake this picture for water or some kind of liquid that is flowing. So if it looks like you have liquid that is flowing this way, you have a stream that's flowing this way, and then you have something like a velocity gradient that exists between this part and this part. That is, you have a velocity gradient that is acting across the width of the stream. Of course, what I'm showing you here is not water or any kind of fluid. It is a set of particles that have been injected into a plasma. That is, each of these dots is a small particle which is negatively charged. So we have all these particles that are moving, and because they are all electrically charged, they all talk to each other through electrostatic forces, and that causes them to move collectively. That is, if I stop this video for a second, if I take any particular particle, if I take this one particle here, if this particle tries to move, its immediate neighbors, because they are all electrostatically tugged together, okay, they all move together. That is, you cannot move one without moving the rest of them, and you cannot move the rest of them without moving this one. One for all and all for one. So this type of interaction where you have a lot of coupling between all these particles is called strong coupling, and these type of plasmas are called strongly coupled dusty plasmas. So that's what we are trying to understand, and it's where our connection with the big picture of nuclear fusion comes. We are trying to understand how charged particles behave inside a plasma. That's the one line. Okay. So we take these electrostatically coupled planes, and if you have taken any basic physics course, if you know that the charge on each particle is Zp, and if you know that the distance between them, if you call it delta, that distance delta is approximately inverse of the number concentration of particles. That is, if you had 1,000 particles, the distance between, average distance between each of them is roughly 1/1000 to the minus 1/3. So this would be the potential energy of the grains because of their electric charge, okay? And each grain also has a velocity. That is, if you have taken mechanics, you know that each particle has a velocity, and you can define a kinetic temperature or a kinetic energy based on their velocity. So you have potential energy and then kinetic energy. And what we want to compare is how much is the potential energy compared to the kinetic energy. That is, what is the ratio of potential energy to kinetic energy? And if that ratio is, let's say, very low, that is, if the grains have more kinetic energy than potential energy, this ratio gamma is much, much less than 1. That is, it's more like a randomly moving particle, which doesn't care about where the other particles are. It's all kinetic energy driven. Whereas if the gamma value is high, or in other words, if Zp is high, you have something that's closely moving together. You cannot move one of them without moving the others. You are more in a state of liquid or solid-like behavior. That is, in a liquid, if you take a droplet out, you would not exactly take one droplet out. You would be taking a little more blobs that are sticking to that droplet, and the same is kind of expected here. So we are used to thinking about matter as solid, liquid, and gas. Like everybody knows this. But the words solid, liquid, and gas themselves are not really real objects or things that you can actually find. They are metaphors for how particles behave together. That is, if you have a set of particles that are closely knit together, like a well-knit family that one suffers, everybody suffers, or one is happy, everybody is happy, you call that a state of solid, where the coupling between them or the gamma parameter between them is quite high. It's more in this range of 10 or more than that. If you have a system in which the particles are sort of strongly bound, but time and again they do evaporate. Like for example, if you have a beaker of water, you do know that if you leave that and come back after 1 week, all the water is gone because of your evaporation. This is because the molecules, even though they are all interacting with each other, they at times are able to fly away separately, and they don't care about what is happening in the rest of the liquid. If you contrast that with a gas, if you had a bottle of air or nitrogen in a cylinder, if you leave the valve open, you do know that within a few seconds or a few minutes, all the gas goes away and mixes with the rest of the air that's in the room. So we are used to thinking about gas, liquid, and solid as states of matter, whereas in reality, these are metaphors or descriptive words for how a set of particles or a set of molecules or a set of ions or a set of grains behave collectively. If they don't care about others, if they just fly in random directions, we can call it, it's more like in a gas-like state. If they do care a little, but they are strongly, still they have some freedom to run away from time to time, we call it a liquid. And if there is no freedom to move, everybody is locked solid in their positions, they don't have much mobility or freedom, they can just stay where they are, maybe move around slightly, little bit from where they are, we call it a solid-like state. So why am I saying all this? The reason I'm saying this is dusty plasmas are an excellent way to study these type of interactions, and that we are able to use them as experimental systems that allow you to observe gas, liquid, or solid-like behavior, and then use theories or advanced mathematical tools to come up with descriptions or mathematical models of how they work, or why is a solid called a solid at this particular temperature and pressure, why does it become a liquid at a different temperature and pressure, and so on. We can come up with explanations for all that, by observing experiments done with dusty plasmas. And in a way, that's what we are doing in this project. So having said that, and having reached 10:22 a.m., what I'm going to do is skip ahead over a lot of details. Okay, basically all this that I have planned to talk, I'm kind of skipping over because that's part of what I think are details. And I want to just show these animations where we have a set of particles and we have a gamma value, which I recall is potential energy divided by kinetic energy. In this case, it's much less than 1. So you have a set of particles that are mostly moving around with kinetic energy. There is almost no force between each other. And that this represents what you would think of as a gas. Like if you think of a set of, like a helium gas, the molecules are randomly jostling around. Like you would see here, it's a visualization of what those molecules would be doing. If you increase the gamma values a little bit, maybe make this around 30, what you get is a set of particles that have some structure to them. That is, they are not totally randomly moving, but they do move a little bit randomly. So if you observe this one particular particle here, it is moving randomly, but it is also not moving away too far. It's still kind of locked in its position. There is some structure, but there is some freedom also. If you ramp up gamma even more, if you go up to, let's say, maybe like 150, what you have resembles more like a solid. You have these atoms that are deadlocked in this position, but within that position, they have some freedom to kind of do a random walk. They go around here and there, and that they don't have too much freedom to do much of anything. We call this a solid-like state. So the big picture is we want to understand the behavior of dust grains when they are inside a plasma. Based on how much charge they pick up and what is their number concentration, what is their kinetic energy, they can exist in a state of collective behavior or in which they are gas-like or liquid-like or solid-like. And what we want to do is to take information about their position and velocity that we can extract and use them to develop, I'll underline this word here, constitutive laws of dense matter. Meaning, if we know the position and velocity of all the particles, we can develop equations for how they behave. Like for example, if you are a student of thermodynamics, you do know that the ideal gas law describes the behavior of gases at high temperature and low pressure. Now, what happens when you decrease the temperature and increase the pressure? From gas, you go into a liquid-like state. Now, what is the corresponding equation for a liquid-like state? If you freeze your liquid a little bit more, you get a solid-like state. What is this equivalent relation like this one for a solid-like state? Those are the kind of questions that we are trying to address through this research here. Okay, so big picture, understand the behavior of grains. Fine details is to use experiments in dusty plasmas, and then the outcome that we expect is to develop mathematical models for the behavior of real materials. Okay, that's what we are trying to do. So I want to acknowledge this DOE Early Career Award. There is also funding from NSF that has helped made this work possible, and a lot of collaborators from really big places and really innovative people that I wish to acknowledge here. And of course, the students who do all the hard work. I have a good group going on here, and especially all the work that I was supposed to show on this talk, but didn't because of I went into a discussion of the big picture is by Mr. Vikram Suresh, who is a PhD candidate with me. And with that, I thank you for your attention and would be happy to answer any questions. Thank you.
Yes. If you have any questions or you have any comments, anything like that, please feel free to add them in the chat function below or the Q&A function or the Q&A box. Either area we can answer questions. But thank you, Dr. Ranga. That was a very informative, and I know it was a little bit rushed, but it was a very informative talk about your research. So Thank you
Thank
so
you.
much. for doing
Thank
that.
you for the opportunity.
Yeah, we'll wait a minute or two for any questions, if anyone has any questions.
Yes, students, undergrads, and I see some familiar names. Let me see.
Yeah.
Here. Alan, Matthew, I know you from the classes. Adrian, Santosh, if you have any questions, Kairos, I think is it Kairos Jones? I know that student. So if you are looking for research opportunities, this is not the only project we are working on. We have 2 more projects going on, and I am looking for enthusiastic students to join our group all the time. So feel free to contact me and we can work something out. Okay.
Yeah, definitely. Well, it looks like we may not have any questions. Would you like to say in the last about 2 minutes here, would you like to wrap up our session with anything you'd like to say about what's going on with your research or the
So
DOE? Have you got anything like that?
I mean, since there are a lot of students here, what I'll say is one piece of unsolicited advice. It's not unsolicited since you asked for it, so I'm saying it, which is a lot of students think they have to be really clever and smart to be able to do research. On the contrary, smartness is not enough by itself. What you need to be is curious. If you can't look at something and question it or come up with something that's worth asking, that is something, come up with something that's worth studying, then there is no real reason for you to do research. You can be very clever, very smart, very brilliant, but if you're not curious, you will amount to nothing, because your curiosity and being honest about satisfying it will make you work hard, will make you answer more questions, raise more questions, and will give you the skills and temperament to get the job done. So if you've thought about research and you're wondering whether you can do this, ask yourself if you are curious enough to pursue something, anything. It doesn't have to be plasma science, it can be anything. But if you don't have curiosity, you got nothing.
There you go. I think that's a great way to end it, and that's great advice for life as well. So thank you all. Our next What's Next series will be next in 8 days, which is next Thursday. Ryan Hughes, excuse me, next Tuesday. It'll be next week. No, sorry. Let me start over. It's next Wednesday, the 9th. I've got my dates confused here. It's next Wednesday, the 9th at 12 or 1 p.m., I believe. It will be Dr. Ryan Hughes, who's one of our Patents to Products fellows. He recently just launched a new startup within the program, so we're really excited to have that, and we will be seeing everyone there. Thank you so much. Bye-bye. Thank you, Dr. Ranga.
Thank you. Thank you all.
Thank you. Bye.